Okay, now let's move on with the third part of our semester review. So basically, let's let's define what thermodynamics is. I mean, like, what is the first law of thermodynamics? Energy is always conserved. So let's write that down right now. The fact that energy is never created or destroyed tells us that energy is conserved for anything that happens. For example, if, let's say, I open the door, for example, this is something that we regularly do, I suppose, right? So here's the door, and I open it, and it has hinges here that turn, or that turn and causes a rotational motion, right? So I'm using up energy to pull this doorknob, right? And this energy that I'm dissipating, it's coming from it's coming from, let's say, chemical reactions in my body, or mechanical energy inside the human body. And this mechanical chemical energy from our body is being dissipated to just move this door, and the energy we're dissipating is going into moving the door and into the rotational motion of the axles. So you could just see in our everyday lives, like, energy is always used, right? So thermodynamics says if you have a system, which you could define like a box or whatever. Let's say you have a box here, whatever. Let's say I have a system or whatever, and this box is my system. Let's say there's gaseous particles in this box, right? Let's say there's gaseous particles in this box, all over the box. And let's say I have fire down here, or I'm increasing the temperature of the system. So the fact that this energy flow into the system won't be wasted, because it would go into the kinetic energy of the gaseous particles. Makes sense, right? So this is basically the first law of thermodynamics. Now in this case, when this system that we defined, if it's gaining energy, it's an endothermic process, right? Endothermic process. And this fire, let's say, it's losing energy because all of its energy is going into the system. This would be an exothermic process because it's releasing heat. Let's say we have a combustion of some hydrocarbon, say CH something, whatever, and the combustion of this hydrocarbon is causing, let's say, heat to flow into the system. This combustion right here is going to be exothermic because it's releasing heat and it's going into the system. And then this would be exothermic, and then the system, the energy that's going into the system, is obviously endothermic. So this is, get a gist of what everything is. Okay, now let me introduce you to the concept of enthalpies of reaction. First of all, you had, like, from before, bond enthalpies or bond energies. Bond energies is the opposite, is the enthalpy of reactant minus product, but the enthalpies of reaction is the enthalpy of the product minus the reactant. Now the bond energies are, of course, the enthalpy of reactant minus product, because bond energies, usually when you have bond energy problems, they give you that, like the bond between H and H, it is at a certain enthalpy. Those are those type of problems. But then the type of problems for enthalpies of reaction, they usually give you in a table, like, the enthalpies of each reactant, each individual reactant. Like, for example, 2H 2G, you would find this in a table. It's called enthalpies of formation, something like that, right? They give it to you in a table, and you find the enthalpies of each. So this forms 2H2. So the entropies of reaction using this, you would first take the product, the entropy of the product, and subtract it by that of the reactant, and then you'll get that the change in entropy would equal to negative 83.6 kilojoules. 0.6 kilojoules. Now let's get into the matter of heat and heat. So basically, one can calculate heat by, for example, if you have a system, if you have a system, right, and let's say this system, right, let's say you have a system and you add, and then this system has water in it or something, has water at 100 degrees Celsius or so, 100 degrees Celsius, and you want to add an ice cube to it. You add an ice cube to it, and then this ice cube is at, let's say, a cold temperature. Say this ice cube is at a cold temperature. Now this, let's say the ice cube is, say, at 5 degrees Celsius. These two systems, let's say the water is the surroundings, right? So this ice cube would obviously gain heat, so it would be an exothermic process. It would obviously gain heat, so it would gain heat from its surrounding, so the water would obviously give it some type of heat to become an endothermic process, and it would gain heat to become in equilibrium with the whole system, right? In this case, the system would be the water. So in this case, we say that the heat of, let's say, the reactant so in this case we say that the, let's say, negative heat of reaction equals the heat of the solution, which is in this case the water, I guess, right? So how do we exactly find this heat? So we basically say, use the equation mc delta T, which is, or mcat, whatever. So you say that mc and the specific heat of, let's say, this ice cube, the ice cube, just label it I, times its changes temperature, its change in temperature would equal the specific heat of the water. Then the negative of this would equal the specific heat of water times its change in temperature. So this is how you would deal with these type of problems using this equation. Now let's talk about bomb calorimetry problems. So bomb calorimetry problem. So I'll abbreviate calorimetry with C. So bomb calorimetry problems. So in order to do bomb calorimetry problems, first of all, to calculate the heat of combustion from the measured temperature, right, increase in the bomb, you must know the heat capacity of the calorimeter, which you call C-cal, right? So first of all, you have this, like, suppose this bomb thing filled with, this is like the most efficient way you could draw it, the bomb, and you have a motor here that constantly stirs the water, so that the heat isn't just trapped in one single area, so it becomes evenly distributed. and you have, let's say, these two rods. One is positive, one is negative, and it's connected to this, let's say, this chamber where it has food or something like that. Food has food in it, and then first of all, these two rods would probably create an electric discharge, and it would create a reaction inside this chamber. This chamber would release heat, which is exothermic, and then it would be like, and this motor would basically stabilize it, and you would calculate the change in temperature of this bomb calorimeter. So knowing the change temperature of this calorimeter, you know that C cal, which is the heat capacitor times the change in temperature, would give you the amount of heat of the amount of heat of combustion of the calorimeter, of the bomb calorimeter. So in order to do these type of problems, for example, let me give you an example problem. So suppose we have butane, and let's say it's in this chamber right here, and there's electrical discharge, and the reaction happens. Let's say the observed enthalpy change is negative 82.61 kilojoules per mole, and we know that the constant, the constant or the heat capacity is 3.98 kilojoules per degree Celsius. So we're supposed to find the change in temperature of this, let's say, this reaction or whatever. So how do you solve for this temperature change? So the equation we all know is that Q equals to C cal times delta T. So can we just use this negative 82.661 kilojoules and plug it into this function, and use C cal and plug it in as well? Well, no, not yet, obviously, because this is in kilojoules. This is in the unit kilojoules per mole, and this Q right here is in the unit of just kilojoules, right? And let's say you were also given that number of grams of butane was 0.2318 grams, right? Was given that as well. So first of all, you would have to find. So first of all, you would have to find the Q associated with this reaction. So since you know that there's negative 82. So basically you could write a stoichiometry equation, since you know that it's negative 82.6 kilojoules per mole of CH4H10, right? And for every 1 mole of butane, you have 58 grams of butane. Let's say 58 grams of butane, and that in this reaction there's only 0.218 grams of butane. Then you solve for the number of kilojoules. You solve for the number of kilojoules of the reaction, right? Which should be probably negative 0.33 kilojoules, and then you would divide that, you would plug that into this equation and divide it by C to get the change in temperature. So you divide that by 0.398 to get a change in temperature of about 0.083, and that's how you would do this type of problem. Thank you and have a nice day. Fall Academy signing out.